This is Science Max, Experiments at Large. Science Max! Greetings, Science Maximites. My name is Phil, and today on Science Max Experiments at Large, we are using mousetraps, but I cannot find my mousetrap, so it's gonna be a little hard to do the experiment unless I have... Oh, hey, here they are. Oh yeah, I stored them preset. Why would I do that? Okay, well that's fine. Anyway, today we, careful, are going to be using mousetrap. Like I said, we are going to be using mousetraps. Mousetraps as a form of propulsion. That's the force that makes things go, and we are going to be making a boat go. And what is the thing that's going to make this boat go? A mouse. Oh, it's not set. Sorry, I'm really jumpy. Anyway, we're gonna be using a mousetrap. And don't worry, no mice are gonna be harmed in the making of this or any Science Max episode, but mousetraps are really great because they can store energy in the spring. If you see, there's a spring that makes this bar want to snap back, but we can put energy into the spring and store it and then use that energy as it unwinds the spring to propel our boat. But it's a little more complicated than just this, so come on, I'll show you. What we're gonna do is build this. This is the mousetrap boat, and it works like this. I've got the mousetrap, and it's attached to a long arm. That arm has a string on it, and it goes around the paddle wheel, and as the mousetrap unwinds, the paddle wheel spins like that, which pushes the boat forward. Now, it looks kind of complicated, but it's actually quite simple to make, and here's what you need. My mousetrap boat is made with styrofoam, craft sticks, and elastics. You'll also want a pencil, plastic drink caps, a shish kebab skewer, small zip ties, string, and of course your mousetrap. Now, mousetraps can hurt your fingers, so get an adult to help you when you use it. Start with 2 pieces of styrofoam. I like to cut mine into this shape, but the only really important thing is that they're the same size. Your paddle wheel is made from a circle of styrofoam with it penciled through the middle, and it will go across like this. To make the paddle wheel, I use cut pieces of craft stick, or they can be plastic, and make some cuts and then put them in like this, and that is what will make your paddles on the paddle wheel, because that's the wheel and that's the paddle wheel. That's why they call it that. Stick drink caps to the ends of the pencil after sticking it through the styrofoam. I like to use a few craft sticks and elastics to help give the styrofoam strength. Next is the mousetrap, which you want to glue down to a frame of 4 craft sticks. Attach the frame to the boat with elastics, then attach the shish kebab skewer or a pencil to the mousetrap with zip ties. I like to put some craft sticks on the end to make it easier to tie the string to it. Wrap the other end around the paddle wheel pencil, and remember you need enough string so that your stick can lie flat. Okay, let's try it out. Wind up the paddle wheel. This will be a little hard as the spring will pull back, but that's where you're storing the energy. And when it's wound up, put it in the water and let it go. The paddle wheel turns because the mousetrap is transferring energy that we put in earlier, and it goes all the way. We stored the energy in the tension of the spring. Now that tension is pulling the mousetrap, the stick, and the string, which turns the paddle wheel and makes the boat go. Mousetrap-powered boat! If you want more detailed instructions or other designs, look up Mousetrap Boat. And there you have it, the Mousetrap-powered paddle wheel boat. And this is what we're going to max out today. Come on. All right, time to pick an expert and go off to max it out. Careful. Okay, let's see here. And, who to pick? Michaela from the Ontario Science Center. She'd be perfect. All right. Come on. I ended up in the water again. Oh well, at least maybe Michaela made it. Oh, Michaela!
Whoa, Phil!
Are you okay?
Are we still fixing the portal?
Yeah, I needed did tweak it just a little bit. It's a little off again. Anyway, great to see you, Michaela from the Ontario Science Center. You're gonna help me max out the Mousetrap boat.
Awesome.
Yeah.
Wait, where's the boat?
I don't have it. I thought it was gonna come through the portal. It could be anywhere, really. I mean, what? Oh, here it is. Okay, good. So here is the Mousetrap boat. Check it out. So got a mousetrap here, right? And you wind up the paddle wheel, and it goes. Yeah, right on.
Awesome.
So what do you think we should do in order to max this out?
Well, first idea, I'm just thinking more mousetraps.
More mousetraps. So we just make a boat and it has like N mousetraps on it.
At least.
Okay, great. Actually, I had mousetraps coming through the portal as well.
Okay.
Oh. Okay. Okay, we're all right. Okay, so now we've got the mousetraps. We can start building. Let's collect them carefully, though. I don't know if they're... Initial thrust or constant thrust. What's the difference? It's all about power. Paper airplane initial thrust. It gets all of its thrust from my throw. Initial thrust. If you want constant thrust, you have to take the thrust with you, like this. There's a lot of cats in here. Initial thrust. Initial thrust. Initial thrust. All the energy is put into the beginning of the... All the energy is put into the beginning. If you want constant thrust, then the thing has to produce power while it's moving. Wind up car, constant thrust. Actual car? Yeah, that's constant thrust because you have an engine. Of course, not this car. This is a toy car. But you know what I mean. Check out this fishing rod, and on it I have a lure with a hook. Now watch this. I cast it out, initial thrust, but then I use the reel and start winding it back in. Constant thrust, huh? Two thrusts in one. And now you know the difference between initial thrust and constant thrust. Hey, I caught a fish. Hey. Oh, easy, kitty. Nice kitties. Easy, Ramona! Michaela and I are maxing out a mousetrap boat. We built a larger version with 10 mousetraps all in a line. So it looks pretty good. I think we're ready, right?
Yeah, I think so.
Got a whole bunch of mousetraps. Should we wind it up and see what happens?
Let's do it.
I think this is gonna go pretty well. What do you think of that stick? Is that gonna bend too much? Is that gonna snap or?
It's pretty flexible.
I mean,
I think we're okay.
I think we just keep going until it breaks. Ooh. Now it's starting to look very fast.
Man.
Yeah, I think it looks like a speedboat. Okay, ready? Go. Well, positive. It is working.
It's not gonna win any speedboat races.
It is not gonna win any races at all. But it's totally working. The mousetraps, they're pulling on the string. The string is making the paddle wheel turn. Just not much. I would have thought this many mousetraps would be a little bit more effective.
Yeah, it looks like we're going for distance over power things. See,
Oh,
we're
right,
using
because-
a lever here. That's a lot of distance for this to travel. But if
Small
we
amount of force over a much longer distance, that's how a lever works.
Exactly.
So we slide the rope down further on the stick, then we would get more force, and it just wouldn't go as long. Okay, so why don't we try that? Wrapping, like that.
Nice.
All right, once again.
Trial 2.
Okay, ready?
Ready, set,
Go! Ah!
Hey, that looked better than last. Oh, now it's picking up.
Yeah, that's really working. Oh, careful. Oh, look out! Look out! So, good. It's good.
Hey.
It's not great. Not yet.
Yeah,
Right? How do we make it better? What do you think?
Well, I was thinking, what if we try to reduce the friction? Remember that other boat we tried?
Here it is.
Oh, yeah.
The little one, you mean?
Yeah, the little one. See, look at this one. It has a pontoon style. Do you see how we have it floating on these two surfaces?
Yeah.
So very little is actually touching the water. Whereas
Oh.
this one, we have a giant hull that's going to drag the water and slow our boat down.
So it's sort of like the difference between like pushing a whole bunch of water like that and pushing the water like that.
Yeah, we want very little resistance. resistance for a boat.
So little resistance with a couple things that just stick down like that. A lot of resistance when we have big, flat, big, like that. So we completely rebuilt this boat. Shall we do it?
Yeah, let's do it.
Our tools floated away again.
Oh.
Race ya! Our maxed out Mousetrap boat isn't the only way to give a boat propulsion. Let's look at another way using a balloon. Let's make a balloon-powered boat. All you need for that is something to be your boat and a balloon. Then you attach them together. Actually, the best way to do it is use a straw and attach the balloon to the straw using an elastic band. And then you attach it to your boat using more elastic bands, just like this. I've put a nice tape top on the boat to make it look awesome. And I also put a little bit of a riser here using just anything plastic to keep the straw nice and straight, because the question is, will our balloon-powered boat work better if it's pushing in the air or if it's pushing in the water? Well, let's do a science experiment and find out. First version, in the air. Oh, almost all the way. Now let's try it with the straw like this so it pushes into the water. Whoa, works so much better. Why? Because water is denser than air. The air coming out of the straw has to push against something to make the boat move. Water has more mass than air, so pushing against water has a better result. Now, let's max it out. This is an air compressor. Well, actually, that is the air compressor. You see, the engine here pushes air into this tank, which works sort of like the balloon. And then it goes out this long hose, which sort of works like a straw. So let's make a maxed out air-powered boat. Ready? Just like the small boat, pushing against the air doesn't produce much thrust. Huh. Not so great. But now let's put it in the water. Pushing against the water gives me much more thrust because water is more dense than air. Whoa. Maxed out air-powered boat! Maxed out air-powered boat! Yeah! Whoa! That's not me. Michaela and I are maxing out the Mousetrap boat. 10 mousetraps didn't seem to make our boat go very fast. But moving the string down our lever arm helped, and now we want to redesign the hull so it has less friction with the water. Check it out! This is the ultimate mousetrap boat. We got 10 mousetraps here. We got our long arm. We have it attached at the right point of the lever, we think. And then we've got two paddle wheels at the back and pontoons.
Yes.
Yeah, so what do you think, Michaela?
This thing is set.
It's gonna be awesome?
Yep.
Okay, ready?
Ready? Let's test it.
Whoa, it's working.
Hey,
It's working.
Picking up speed.
Yes.
Wow.
Whoa, mousetrap boat. I mean, it's good. It's good. It's not Science Max good.
Yeah. We were hoping it would go faster.
Faster
No.
or... No, pretty much just faster. Yeah, okay. Obviously, we need to store more energy. That will make the paddle wheels go faster, right?
Yeah, so we just have to think about it, right? Like, what's stronger than a mousetrap?
Well, 10 mousetraps. That's why we have 10 mousetraps, Michaela.
Okay, what's stronger than 10 mousetraps?
11 mousetraps? Like, if we just keep going and
Okay,
it's
enough
gonna
with
get
the
super
mousetraps.
wide, we'll have 1,000 mousetrap wide. What?
Enough with the mousetraps. Have you ever seen, like, a rat trap?
No?
They're huge.
Well, hold on. I can just get one from the portal. One rat trap coming up. Oh, okay, came from, all right, well, that's fine. And, whoa!
Wow!
Yeah,
look at
that is a lot bigger. Okay, so
Huge
snap
difference.
yours.
All right,
Is it?
ready? Mousetrap.
Okay.
Okay.
That's terrifying. So that's a lot more power.
Yeah, a lot of force.
So tell you what, we have a little mousetrap boat. Why don't we build a little single rat trap powered boat and we'll race them, and we'll just see the difference in power from one rat trap to one mousetrap.
I like that. We'll do a prototype before we make a big one.
Yeah, okay, come on, let's go. So, we built a rat trap boat to race the mousetrap boat. And then Michaela and I got a little competitive.
Check out the rat trap boat.
No, check out the mousetrap boat. Mousetrap boat is better because...
Yeah, rat trap boat is better. It's got bigger springs, more potential energy stored in here.
And mousetrap boat has less potential energy and less springs, but he's got more heart, and he really wants to win.
Hey, yeah, I'll tell you what, Phil. Loser jumps in the pool.
What? Oh, Okay, sure, let's do it. Okay, ready? Go!
So, as you may have guessed, the rat trap boat has a lot more potential energy that can be stored in the spring.
Okay, so rat trap boat is clearly better than the mousetrap boat. We make the boat the same way,
Yeah.
but we use rat traps instead of mousetraps. What do you say?
Love it.
Okay, let's do it.
Let's do it.
Yeah.
Wait a second, Phil.
What?
Ferris Ferry, gotta jump in the pool.
Okay, fine. Here you go. Hold this. Inertia. What is it? Well, it's directly related to Newton's first law of motion. An object in motion tends to stay in motion, an object at rest tends to stay at rest. Let's do an experiment. Here is an object. Right now, it's at rest. You might think that means it has no inertia, but that's not true. Inertia just means an object's tendency to keep doing what it is doing. Right now, it's doing nothing. But if I wanted to overcome its inertia, I would have to put energy in. And now that I have, it is moving on its own. It has inertia. If I wanted to stop it, I would have to overcome its inertia, its tendency to keep moving. There. I went exactly that far. Now, let's max it out. I'm adding these weights to the cart. Now it has a lot more mass, which means it has a lot more inertia and its tendency to do nothing. But this time it has a lot more inertia. If I wanted to get it going the same speed as before, I'd have to put in a lot more effort. There, now it's going the same speed as before, but now it has way more inertia, so stopping it will be harder. So there you go, inertia. A thing's tendency to stay moving or stay still, and the more mass, the more inertia. Dear Phil, I can't believe you did a whole episode on boat propulsion and you didn't use the greatest thing out there for making a boat move, a propeller. Sincerely, a fan. Well, let's talk about propellers. Oh, good thing this is fan mail. Get it? Because it's a fan? Yeah, anyway. A fan pushes air just like a boat propeller pushes water. They're both fluids and they behave in the same way. Now, if you look closely at a fan, it's curved on the blades. The air or water is caught under at this side and then it's pushed out on the curve to make it go that way. And the faster it spins, the better it works. Now, this is a propeller-powered boat. And what you do is wind up the propeller. I have an elastic band here to store the amount of energy I put in. And then you put it in the water, the propeller spins, and the boat goes forwards. It's being propelled by the propeller. That's why you call it that. Awesome, right? Well, now we'll max it out. This is a drill. It spins. And this is a propeller, and when you put it in the water and spin it, it provides thrust. So let's try it out. Whoa!
Remember not to try this at home. I am a trained professional.
This is a very small propeller. Let's compare. This is a super maxed out propeller. Whoa, okay, let's try it out. Whoa!
The larger a propeller is, the more energy you need to turn it, and the more propulsion you get out. Michaela and I are maxing out the Mousetrap boat. Well, actually, we can't call it a Mousetrap boat anymore because now we're using rat traps. The design is the same as our 10 Mousetrap boat.
Rat trap boat! Rat trap boat! It's the super most rat trap boat ever!
We wind it up and try it out.
Okay, ready? Go!
It worked great. The reason is because this boat was storing a lot more energy in the spring tension. More energy means more propulsion. so much, we couldn't even catch it.
Yeah! Rat-trap boat! Science Max, experiments at large, rat-trap boat, high five. Let's do it again. Hey, welcome to Science Max, experiments at large. I'm Phil McCordick, and hold on a second, I'm just gonna change. Okay, that's better. Now, where were we? Oh, right. Let's go make a boat. So you know that some things float and some things sink, like rocks, or wood, or full water bottles and empty water bottles, or carrots, foam, waffles, screwdriver, playing cards, plasticine, tinfoil, potato, my watch. Wait, that wasn't supposed to go in there. So how do you make a boat? You make it out of something that floats, right? Well, most boats are actually made out of metal. Tinfoil is metal and, well, it sinks. But if you fold tinfoil into a boat shape, it floats. And boats don't only float themselves, but they can hold people and cargo. In fact, there's container ships crossing the ocean at this very moment that are holding thousands of tons of cargo, and they're all made of metal, which doesn't float, it sinks. So how do boats do it? Are they magic? No, of course not. Boats are science. And here, you can be science maximites. Get some tinfoil and cut it into the same size pieces and fold a couple different shapes of boats and see which one can hold the most weight before sinking. And now it's time to max it out.
But before we do, here's how you can fold your own tinfoil boat in less than 15 seconds. First, take a square piece of tinfoil, then fold it in half. Fold one corner down and the other corner down. Then open it up and ta-da, you're done. If you want instructions on how to fold a more complicated boat, go to our website.
I have a feeling I'm gonna need a few extra lab coats for this experiment. Like I was saying, let's max out the tinfoil boat and find out a little bit more about why boats float. Okay, well, I'm here at an indoor pool, which is not, I wasn't expecting to be in the pool just yet, but this is where we're gonna build our giant tinfoil boat, so why not? Who's Nia?
Phil, you're wet.
I thought I was gonna come in over there, but I came in on the water sled. I think I had the coordinates wrong. Anyway, this is Husnia, and she's from Let's Talk Science, which is all about science education, right?
Yes.
Just like us. So you're gonna help me max out the tinfoil boat. I think I dropped it in the water. Hold on. Whoa! Here, where? There it is. The tinfoil boat. The tinfoil boat.
Phil, this is a boat?
Well, it looked a lot better before I came down the water slide, but that's the idea, and then we make it bigger. What do you think?
I don't think it's gonna work, Phil.
Oh, well, why not?
Tinfoil is very thin, and it might not hold the shape of the boat.
Well, I still think we should use tinfoil, though.
Why?
Well, because the small experiment was tinfoil, and I bought all of this tinfoil.
Then let's do it.
Tinfoil?
Tinfoil?
Okay, high five. I will, I'll take the tinfoil, and you take that, and I'm gonna have to dry off at some point.
Welcome to Shipbuilding for Pirates. I'm Swubby, and I've built some of the finest pirate ships for some of the finest pirates this side of the Caribbean. And I can teach you to do the same. But first, you need to know your basics. Mass and volume. Let's start with volume! But not that kind of volume. Which of these two chests do you think has more volume? Right, this one here. Which of these two balloons do you think has more volume? Right, this one here. Volume is how much space something takes up. Which of these two chests has more volume? That's right, they're the same. But which of these two chests has more mass? Which is heavier? Hard to tell, isn't it? But what if I told you that this one was empty and this one was full of treasure? Oh, loonies. Now, which one has more mass? That's right, this one. These two chests have the same volume, but this one has more mass. This chest has more volume than that one, but this one... My loonies! That chest does not have as much mass. Volume is how much space something takes up, and mass is how heavy something is. And when you look at them both together, you're looking at density. Join us next time on Shipbuilding for Pirates, and then we'll look at how volume, mass, and density work together to make something float. Oh, my precious, precious loonies. Are you all right, my pretties? They can't talk, so I'm not sure what they're saying.
So, Husnia and I get to work constructing a large tinfoil boat. Our first design is just sort of a square, folded together out of a very large sheet of tinfoil. Simple, but can I ride in it?
There we go. A giant tinfoil boat, just my size. Woo-hoo-hoo-hoo!
I don't know if it's gonna work. It's too thin.
You think it's too thin?
I feel like yes.
What should we do?
Do you want to test it?
Let's test it. Okay, good idea. So here's the most important question. Do you want to test it or should I test it?
No, you test it.
All right, here we go. Putting it in. First test, does it float on its own? Yeah! Floats on its own, no problem. If I just get in very carefully, then it will work fine. See, if I'm careful about how I get in, no, it's fine. See, if I just get in like that.
Oh my... Bill, are you okay?
Wait a minute. It's sort of, no, that's just air. You know what went wrong? It wasn't boat shaped. I think if we make it look more like a canoe, because canoes float, if we make it look like a canoe, it'll work great.
No, Phil. We need some support. If we add a couple of structures in between, then we add support to it.
I'll tell you what, let's make a boat like I want to make and a boat like you want to make, and we'll see whose is the best.
That's a good idea. Okay, let's do that.
All right, let's do it.
Welcome back to Shipbuilding for Pirates. I'm Swubby, and now we know what volume means, what mass means, and that together it can tell you something's density. Now let's find out why things float. Let's say we're out to sea and my treasure chest gets swept overboard. Oh no! But it's all right. It floats because it pushes enough water out of the way, displaces it to carry its mass. But what if my treasure chest had more treasure in it? Well, we're giving it more mass, but not more volume. Too much mass and not enough volume, and it will sink. Oh no, my loonies! You need more volume if you want to float more mass. And that is why things float. I'm Swubby, and thanks for joining me on Shipbuilding for Pirates.
So, the first version of the tinfoil boat didn't work out too well.
Like that.
But my idea is to build a tinfoil boat more like a canoe to see if a different shape makes any difference.
Tinfoil canoe!
Very Canadian.
Very Canadian. The canoe part, anyway. I don't know about the tinfoil part. So, Husni and I had a bit of a disagreement of why the last boat didn't work. I thought it was because it wasn't shaped enough like a boat, so this one looks like a canoe.
What I thought is that it requires some structure.
Structure so that it wouldn't fold together.
That's right.
And we'll see how it goes.
All right.
All right, here we go. Did it work?
Nope.
Okay, your idea next. Did you know it's easier to float in salt water, like in the ocean, than it is in fresh water, like a lake or a pool? That's because not all liquids are created equal. They have different densities. This is fresh water, or it doesn't have anything in it. And this
is sugar. If I was to put 1 scoop of sugar in this water and stir it around until it dissolves, now this liquid is more dense than before I put the sugar in. Here's an experiment you can do at home using liquid density. This glass just has regular water with yellow food coloring in it. This glass, green food coloring and half a cup of sugar in it. This one has a full cup of sugar in it, and this one has 2 cups of sugar in it. Now, when you do this at home, you'll definitely want an adult to help you because you have to heat the water if you want to dissolve that much sugar in 1 glass of water. I'm gonna put them all in 1 container. You can do this at home, and when you do, I suggest you use a very small container because you have to be very careful when you put the layers in. You can use a turkey baster or a straw. When you put your finger on top, the air pressure will hold the liquid in and you can just drop it in. But these kind of take some time, so I'm going to use the syringe of science. I'm gonna use the most dense liquid first because that's the one that's gonna want to be on the bottom. I carefully put it on the bottom of the container. The next layer, be very careful. And you'll see that the red and the blue aren't mixing because they have different densities. The blue is heavier than the red. We'll add the green, and you can see even when it drips into the red, it comes back up to the top because the green liquid isn't as dense as the red liquid, and the denser liquids push the lighter liquid up. And now we're gonna add the yellow, which of course has no sugar in it at all. And there you go. All the layers stay separate. If you put it on a light, you can really see it. Liquid densities. Now, let's max it out. Ta-da! The longest length of liquid layers. 12 liquids all organized by density. Starting from the bottom, we have honey, corn syrup, chocolate syrup, maple syrup, dish soap, whole milk, water, dyed blue, vegetable oil, extra virgin olive oil, rubbing alcohol, baby oil, and lamp oil. Liquid density. I really want to mix it up, but it took me a long time to make this, so I'm not going to. Our first 2 attempts at a tinfoil boat haven't gone so well. Husnia's idea is to make a tinfoil boat and add some more structure, because the tinfoil just wants to collapse when I get in it. So we start with a large piece of cardboard on the bottom, then we wrap the tinfoil around it and shape it into a boat. After that, we add some supports across the top to stop it from folding in when we add my weight to it. This boat feels a lot stronger than the one I was just in.
I told you.
So how does all of this work?
So we got some support using broomsticks and then some cardboard paper. And then underneath we have cardboard.
And so how will all of this help the boat not sink with me in it?
Right. The broomsticks will prevent it from folding this way and you won't sink.
Good.
The cardboard will prevent it from folding this way and you won't sink again.
Not sinking is my favorite thing to do in the tinfoil boat. All right, so let's try it.
Let's do
now,
it.
Are you gonna get in this one?
I'll tell you what, Phil. If you get in and you don't sink, I'll go after you.
Deal.
All right.
All right, here we go. It's sort of working. Oh no, water's coming in. It's sort of working.
It's almost working.
Uh-oh.
Wow.
No!
Hold on.
1, 2, 3, go! Another thing I learned is that a very light tinfoil boat can be very heavy when it's full of water. I don't know if fixing it is in the cards. I think we're gonna have to build another boat. So what do you think we should do?
Let's add more structure.
More structure?
Oh, yeah.
What if we add like a metal rod around the outside and maybe some more metal rods and ribs? And we wrap it all in tinfoil, and you think it'll work?
Let's give it a try.
Let's give it a try.
Don't worry about it. I got this.
No, I get it. I'll get it.
Sure?
Oh! No, I'm serious. You may have a little brother or sister at home, which means you probably know where you can find some diapers. But there are two things you need to remember. First, ask an adult if you can use the diapers for your experiment. And two, only use unused diapers, okay? Okay. So, you take the diaper, and if you cut it, be very careful, maybe get an adult to help you, over some black construction paper, like I have here, and you shake the diaper over the construction paper, you'll see that there's a little powder that comes out. And this is the secret ingredient. This is super absorbent gel. What it does is it soaks up all the liquid, and diapers are full of them. And you carefully pour it into a plastic cup, like that. Now you can see I have already done it with a number of diapers. It's important to use a plastic cup because it's a little messy, although it's non-toxic, it's totally safe, but it's still easier to clean up by just throwing the cup away. Now, add some water, and what happens is this super absorbent gel absorbs the water and turns very quickly into a paste. Look at that. Now, let's max it out. 5 kilograms of super absorbent gel, 500 liters of water. Now, it is time to do science! And I have my own stir stick. Yep, definitely coming along. I'm not exactly sure if we're getting anything on this camera, but I want to make sure it's recording. Yep, it's recording. There we go. It is definitely turning solid. Well, there you go. The giant super absorbent gel experiment. Corey, Trevor, I need some help getting out. How many outfits have I been through in this episode? How many outfits have I been through in this episode? Anybody have a towel? There you go. Thanks, buddy. That's great.
Husnia's idea of adding structure to the tinfoil boat was definitely right. We just needed to go further. So we did it again. This time, we made a much larger boat. We started with a sheet of cardboard, then wrapped the tinfoil around and added some metal supports taped to the cardboard across the boat this way to make ribs, as well as some other supporting pieces in the front and the back. Then another metal rod all the way around the top, and finally, supports across the middle.
All right, feel how strong it is. I'm really excited about this version of the tinfoil boat. What we did is we used thwarts, big hard pieces of wood that we did last time, but this time we have ribs.
Ribs, right, which are made of a cardboard, a metal rod attached to it,
and shaped, and we did a whole bunch of them that go the whole length of the boat. And then we used all of this bendable metal, and we have one that runs all the way around the gunnels, and a whole bunch that run down the inside, and we even used bike fenders at the front and the back of the boat to give it super rigidity so that it hopefully won't go like all the other boats have done so far. Are you ready, Husnia?
let's do this.
1, 2, 3, lift. All right, let me get over. It floats, but that doesn't tell us anything because they've all floated at this point. It's only when I get into it. Okay, here we go. All right. Hey! Hey, it works! All right.
Oh, it's working.
Ha 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 ha! Look at that! It works perfectly! The tinfoil boat experiment has been done. Science Max, experiments at large. What do you think, Husnia?
The only reason I got into this boat because I knew it's gonna work.
Really?
Oh, yeah.
So you knew you would never get wet? See, I don't think that's fair. I think it's time that you got wet. I think we should go. I think you and I should just get wet right now. Just need.
Someone help.
You're still dry, aren't you? That is so unfair.
Greetings, Science Maximites. My name is Phil. And I am Opposite Phil. Opposite Phil. That's right. Blue lab coat, yellow shirt, evil mustache. I see. Anyway, we're looking at opposing forces today. That's forces that make things go down and forces that make things go up. Right, things with more density and things with less density. Gravity and the opposite, which is anti-gravity. Anti-gravity isn't really a thing. Well, I have to do the opposite. Right. Buoyancy. And buoyancy's opposite, which is girlancy. No, girlancy is not the opposite of buoyancy. You know, you're not helping. Right, not helping. Opposite. Haha. Hello. Goodbye. Hey. Today we're going to be making a gravity-powered boat. Ta-da! It's pretty easy to make. You just put water in the top here. Gravity of the water pushes it out the straw, and the boat goes forward. And it's super easy to make. You only need 4 things. A piece of styrofoam, a plastic cup, craft stick, and a straw. And the tools you'll need: a pen, a craft knife, and the help of an adult, and science glue. Which is the same as regular glue, except I only use this glue for science. You take your styrofoam and you cut it into a boat shape. That requires the knife and the help of the adult. Then take your cup and draw the circle that your cup will sit in. And then you want to put 2 slashes with your craft knife in there. Again, get the help of an adult if you need it. And then start carving out the styrofoam with your finger and make a nice little indent just like this for your cup to fit in. See? And then it fits in nice and snug. So then what you want to do is you want to make a hole in the cup. You can use a pencil. The hole has to be just big enough for the straw to fit in. First, you want to take the straw and dig up in this direction so that it will be a nice angle for the water to come out, and then you want to get the straw back up into the cup like that, and then glue it so that it is not going to leak any water. And then in the final step, and this is your choice, you don't have to do this, but you can use your craft stick and you can make a rudder, or if you want, you can make a whole keel, which goes just like that, and it is right in the middle of the boat, and this helps the boat go straight because sometimes the straw goes off to the side one way or the other. Okay, water-powered boat. Actually, it's a water and gravity-powered boat. You see, what you do is you fill up the cup with water, and the gravity of the water in the cup pushes it out the straw, and the boat goes forward. And this is what it looks like in the water. You fill up the cup, and the gravity pushes the water out that way. The buoyancy of the boat keeps it afloat, and good old Newton's third law: for every action, there's an equal and opposite reaction. The water going out the straw this way pushes the boat that way, and it works pretty well. Whoa, if it's going straight. That's why we have the keel. Okay, so gravity-powered boat. Time to max it out. But first, I need an expert to help me. Oh, of course, Michaela from the Ontario Science Center. Perfect. All right. And let's go. No! I stopped myself. I didn't get wet. Now I'm just gonna get it. No! Oh. Hey, Michaela! From the Ontario Science Center, how you doing?
Good, how are you?
That was the best portal malfunction ever! I'm glad you're here, because I need your help maxing out this. The water gravity boat. It's pretty awesome, and what you do is you put the water in the boat, and then it does this, and it propels itself along. So, we're gonna max it out and make it super awesome. So what do you want to do that?
Oh, man, well, what if we just think about making everything bigger?
Okay.
Right? Like, first we're gonna need a bigger container.
Okay, well, that's a good idea. Tell you what, I got my waterproof portal ordering device. So I'll order some sort of a bin?
Yeah,
Like a big
yeah.
plastic bin. Okay, hold on.
That'd be cool.
Hold on. Here it comes. Oh, there it is. Okay, so a big plastic bin.
Yeah, and then, you see this straw here? What if we had something like that, except bigger,
Like a pipe of some sort?
yeah, like a big pipe.
One pipe coming up.
I need to get myself one of those.
Yeah, but it doesn't always work, so. Oh, here it is.
Wow.
So, bin is the cup,
Yeah,
pipe is the straw.
yeah.
So now all we need is the boat.
Yeah, the platform itself. I think we need something that's gonna be really stable because we're gonna have a lot of weight this time.
How about like a surfboard or one of those stand-up paddle boards?
Hey, that's a good idea.
Yeah, okay, check this out. Uh-oh,
Oh no,
water stopping.
that doesn't look good.
I think it might have gotten stuck.
Oh,
We'll have to go get it. Because the water's still running and that might overflow,
man, it's
so.
stuck somewhere.
Buoyancy is the tendency for things to float. Things like this balloon or this ball in water. But it doesn't float on its own. The helium is less dense than the air molecules around it, and they fall past the balloon and push it up. The ball is less dense than the water around it. So the water molecules flow around the ball and push it up. This happens because water is a fluid. The particles flow around each other. This works because air is a fluid, and I know what you're thinking. You're thinking, Phil, air isn't a fluid, but it is. Usually we think of fluid as meaning a liquid, but in this case, fluid means anything where the particles can flow around each other, and that includes air. But you know what? It's hard to see the particles in water. Same thing with air. I can say it, but it's really hard to see it. Now this is sand, and it behaves like a fluid too. Well, sort of. Check it out. Look, it's made of a whole bunch of very fine particles, and it takes the shape of its container. But watch this. I put a ball in the sand, and it doesn't float. Now the ball is less dense than the sand, but it doesn't float because the particles of sand have a little bit too much friction right now. But watch as we move them around and reduce the friction by adding some air. Now, this sand is behaving like a fluid, and the ball floats. Let's see what else floats on sand. How about this pumpkin? Yup, that floats. How about this block of wood? Yep, that floats too. How about this styrofoam ball? Yeah, that definitely floats. Look at that. The sand is a fluid right now because all of the little particles of sand are moving around. But watch this. If I turn off the air, everything freezes in place. Nothing floats anymore because the sand is no longer behaving like a fluid. So there you go, buoyancy. It all depends on the density of the thing and the fluid it's surrounded by. Huh? Science. Michaela and I are maxing out our gravity-powered boat. We had a bunch of maxed out materials. We just needed to get our surfboard. So we got our giant bin.
We got a giant tube. Water's gonna come out of this end.
And we've got a valve here, which means we can fill the bucket, and then we can turn on the valve and see what happens. So,
Whoa. Hey.
okay, you ready?
Yeah.
Now we're gonna turn on the valve, and that means now the water is flowing through.
Ooh.
Hey, it's working.
Not bad.
Right on. Whoa, look at that. This thing is really working.
Yeah, it's taking off now.
So, okay, this is good. It's going about walking speed. Now that it's working, how do we max it out?
Our fuel here is the water, so
Yeah.
what if we just had even more water?
And it doesn't last long, does it?
Yeah.
Maxing out our boat even more is easy. A bigger bin for more water, and a wider pipe to move more water for more thrust. Okay, so a bigger bin
Yeah.
is a lot harder to fill because it's hard to get to the top of the...
Well, you're working against gravity, so it's gonna work for us.
I can really appreciate the amount of water that we're putting into this. That's 4 buckets full.
Wow.
This is 5 buckets.
We open up the valve and it starts to go.
Yep,
Working.
it is working. Look at all the awesome
Check
bubbles.
that
Okay,
out. That works really well.
it really, yeah, it's definitely
Wow.
faster than the other one. I think it's the larger pipe, and we need more water because it doesn't last very long.
Check it out. It looks like it's going even faster now that we've lost a bit of the water.
Less weight.
Yeah.
This is working great, so now how do we make it even better?
Okay, well, the only force working with us right now is gravity, right? Of
Right.
the water coming out. What if we add in an extra force?
And we could squish the water down to go out faster. Okay, watery high five. Okay, we gotta get it's way over here. Come on, we gotta get it. I want to move the water from this container to this container. Now, I could just pour it, but what if it's too heavy? It's too heavy! Help me, science! Well, science to the rescue with this! A clear plastic tube! Ooh, science-y. Okay, watch this. I'm gonna make a siphon, and it's pretty complicated, so follow along. Are you ready? I stick one end in here, and one end in here! Whoa! Yeah, I know, it's not working yet, but that's because we haven't added the science. First, we need to add a little bit of suction and suck the water through the hose like a straw. It has to go over the highest point. Watch this. And there we go. Look, the water is going up. I can even make the water go up even more, and it still works. But why does the water go up? Water doesn't like to go up, right? Well, the reason why is because there's more water going down than there is going up. So that creates suction on this end, and the gravity of this water pulls that water up. So gravity is doing all the work for us. And that is a siphon. Huh? So now let's max it out. This is the same container of water, but now it's colored slightly blue so you can see it go all the way up through this hose. The only really hard part about this is sucking the water all the way up to there. Okay, here we go. I got it working. Now, the reason why it's working is because there's just a bit more water on this side of the tube than there is on this side of the tube.
With a siphon, it doesn't matter how far you go up, as long as the water on one side is lower than the other.
Science. You know about helium balloons, right? Helium is a harmless gas that is less dense than air, which is why helium floats.
If I was to breathe some helium, my voice sounds higher because helium is less dense than normal air, so my vocal cords vibrate faster. Ah!
But have you ever wondered, is there a gas that's more dense than air? There is.
It's called sulfur hexafluoride, and it's much more dense than air. So if I was to breathe some, my vocal cords would vibrate slower, making my voice lower. Ha 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 ha!
This container is full of sulfur hexafluoride. Ooh, I know, it's invisible, you can't see anything. But watch as I blow some bubbles. The bubbles are floating on top of that layer of sulfur hexafluoride.
The bubbles float because they're full of regular air, which is less dense than the sulfur hexafluoride.
In fact, a balloon will float on this as well. The balloon floats lower because the weight of the latex also drags it down a bit. But the bubbles and the balloons are floating on a sea of sulfur hexafluoride. And it is like a sea because it's a fluid just like water, but it's more dense than regular air.
Science! It's awesome!
Michaela and I are maxing out our gravity-powered boat. It was already working well, but now our idea is to try squishing out the water so it gives the boat more thrust. We just had to come up with a brilliant idea how to do that.
Garbage bag! Garbage bag! Yeah, garbage bag! Okay, maybe we should explain the garbage bag. Okay, so the garbage bag is attached to the pipe at the back end. There's a hole in the garbage bag. Well, we fill the garbage bag with water. Then we tie the garbage bag tight. Tie the knot so the air doesn't get it. Now that we've got that, we use bowling balls! And we put the bowling balls on top of the garbage bag, and this will, squish the water out
really is pushing on that bank.
Okay, ready? Okay, let's see.
Hey, it's moving.
Our bowling balls were squishing the water out, but the boat didn't seem to be moving much faster.
I think the bowling balls made the whole thing too heavy.
What if we raise the bin up?
If it's higher up, then there would be more force due to gravity.
Yeah, so we have the bin on like stilts or something,
Oh my God.
and then it has to fall further, and then maybe the water's going faster.
I love that idea.
Okay, good.
Yeah, let's try it.
So what we need to do is get
Wait,
this.
no.
Oh, I thought this is the shallow
No,
pool.
yeah, no, that's
that
over
one's
there.
that
yeah,
one. Yeah.
not here.
Max Historica. Long, long ago, in the time of ancient Greece, there lived a genius named Archimedes. One day he was in the tub and he noticed something.
Oh, hello. Look at that. When I get into the tub, the water level goes up, and when I get out of the tub, the water level goes down. Ha ha! Eureka!
I, don't get it.
Well, I can calculate how much volume something takes up by how much water it displaces.
Yep, still not with you.
Now, I'll give you an example. How much water would be displaced, pushed aside, if I put this ball in the water?
It's light, so not much.
Ah, it doesn't matter how heavy it is. It only matters how much space it takes up. Watch. Ha! You see? The same volume, huh?
I think I see.
How much water will be displaced when I put this bowling ball in?
More because it's heavier.
Ah, nope. It doesn't matter how heavy it is. It only matters how much space it takes up. Watch.
Oh.
You see? A simple and easy way to measure something's volume.
Archimedes, one of the greatest and cleanest scientists in history. Join us next time for more Max Historica. The metric system in 60 seconds.
The metric system is a way of measuring things. Water boils at 100 degrees Celsius, a kilometer is 1,000 meters, but few people realize just how interconnected the metric system is. First of all, it breaks down to a base 10 system. Everything is 10, 100, or 1,000 of everything else, and it's all based on water. This is exactly 1 liter of water. It weighs exactly 1 kilogram. It fits into a cube 10 centimeters on each side. It boils at 100 degrees Celsius and freezes at 0. And this happy little fellow is 1 milliliter. It fits into a cube 1 centimeter on every side. It weighs exactly 1 gram, and the amount of energy required to raise this 1 degree Celsius is 1 calorie. The metric system, everything interconnected and all based on water. Ha! Oh. Uh-oh.
Michaela and I are experimenting on our maxed out gravity-powered boat. Trying to squish the water out with bowling balls added too much weight for it to make much of a difference. So now we've raised our tote higher up, which means the water will have farther to fall and be going faster when it comes out.
And I got a totally awesome name for our boat.
Tell me, what's up?
Totes McBoats.
That's a totally awesome name!
Totes McBoats? Yes! Okay, so are we ready to fire up Totes McBoats?
That's right, yep.
Okay, I'm gonna turn on the valve. Okay, ready? And let go. Totes McBoats!
What we hadn't considered is that much weight that high up would be tippy.
Totes McBoats no longer afloats.
We needed a way to solve the tipping problem first.
You know what we need to do?
What?
We need to build an outrigger.
All right, so check it out. This time we have an outrigger, which means our boat's gonna be a whole lot more stable. It's not gonna fall that way because this thing is floating, and it's not gonna fall this way because it has a lot of mass as well. Think we're almost ready, eh, Phil?
Yeah. Okay, are you ready?
Ready?
Okay, let's do it. Turn on the valve.
Here we go.
Go, Totes McBoats. Oh, yeah. Yes. Yes. Totes McBoats. Oh, the outrigger's pulling it to the side. Oh, in this way. Yes. It goes really fast.
Our gravity-powered water boat worked great. The water ran down from high up, giving it more speed due to gravity, but no more mass than before. And our outrigger kept the whole thing from tipping over. Totes McBoats was a success.
Thank you very much, Science Max Experiments at Large. gravity-powered boat, otherwise known as toad stick boats! Toads, come back, toads! Come back! Greetings, Science Maximites. Take a moment and imagine with me, if you will, a time when the only way to light your house was with candles or oil lamps. There was no electricity. That meant no power tools, no video games, no telephones, and worst of all, no TV. Fortunately, we live in a world of electricity. If you've ever lost power in your city or neighborhood, you know how hard it is to get by without electricity, even for one day. But where does it all come from? Where do we get this electricity that we use all the time? We make it. That's the cool thing. And I can show you how to make it as well. Check it out. All you need is an electric motor. Electric motors are pretty simple. All you do is get a battery and you attach it to the electric motor, and that makes it work. There we go. Attached to the battery, it spins. But if you spin the electric motor, it creates electricity. And that's what we're gonna look at today, creating electricity. We're gonna build a wind turbine. But first, you need an electric motor. And you can probably get one from a broken toy. Just make sure that the toy is broken and that the broken part isn't the electric motor.
Here's what you need: index cards or construction paper, scissors, push pins, science tape,
It's the same as invisible tape, except I use this one for science.
a cork, chopsticks, craft sticks, and modeling clay. And remember, all the steps for this experiment are on our website. To begin, cut the index cards into strips and tape down a push pin so it sticks out. Then fold over the index card and tape it together. Then stick the pin into the cork and repeat that step.
If you want as many blades as you can get on your fan, you're welcome to do that.
Next, take your modeling clay and stick the chopsticks in, then tape the craft sticks in between with science tape. Then take the motor and stick the cork on the end, then wedge the motor in between the craft sticks and tape it down so it stays put.
And there you go, a fan that will spin in the wind.
You want to adjust the fan blades so they all face on a bit of an angle. That way they will catch the wind and spin.
There we go. Now when it spins, it will create electricity. I'll show you with this. It's a multimeter. And a multimeter measures little amounts of electric current. There. The hairdryer makes wind, spinning the fan blades, and we are creating electricity. Now, pretty much all electricity that you make comes down to turning a generator. A small motor like this isn't gonna produce a lot of electricity, barely enough to power one tiny little LED, but it's a start. And a good start is all we need, because today on Science Max Experiments at Large, we're gonna look at all kinds of different ways of generating electricity. Plus, I wanna find out just how much electricity one human being can generate. Although one human being is gonna be kinda lonely, I'm gonna need an expert. Oh, I know, Anthony from the Ontario Science Centre. He can help. I wonder if he's busy. Well, come on. Oh, Anthony! Phil? So I was wondering if you could help me with an experiment. I want to generate as much electricity with human power. What do you think?
I think that sounds awesome.
Okay, great. Let's go back to Science Max headquarters.
Is that the portal?
Yeah. Don't worry, all the kinks are worked out. I know what it is. It's this. Where did you end up?
I was in the vents.
Oh, I ended up in the bathroom. All right, well, now that we're here. Okay, so this is what I started with. And this is just, you know, an electric motor, right?
Right.
So you can generate electricity, you spin it, so I figured in order to generate more electricity, you get a bigger generator?
Exactly, yeah. The bigger the generator, the bigger the magnet, the more the copper, the more the electricity.
Oh, well, you know what we should do is we should just get an even bigger one, like a giant one that they use in like at a power plant or something, or?
Not quite. That would be too big for a person to be able to turn. It'd just be impossible.
So you think this is a good size?
I think this is great size.
Okay, so that's good.
This is called a multimeter. We're gonna hook up the wires. I will do black to black.
Black to black.
To red. And as you turn our generator, we can see just how much electricity we're generating. Okay, so.
Here, you hold on to that.
This,
and
you
I'll
can
turn
start
the
turning it.
generator. Now it's time to play How Much Electricity Did They Make?
2.4 volts, yeah, it's not bad.
Oh, 2.4, yeah, it's not great.
That's just enough to power a small LED flashlight. Better keep trying, boys.
I got some handles here that we're going to attach
that
to
would be
the
perfect.
end of the generator so
Yeah.
we can spin it.
Okay, let's try.
No matter how fast I cranked the large handle, I couldn't make any more electricity than before.
Okay, let's try something else.
But it's a smaller handle.
Perfect, okay, yeah.
That's good?
Yeah, well, maybe it'll let us get more spins in.
Oh, yeah, because I don't have to make as big a circle.
Exactly. Yeah, it's working already. We're up to like 3.5,
Now, how much electricity is Phil making?
4.5.
That's the same as 3 AA batteries. Maybe enough to power a toy car. Still a long way to go.
Yeah, it's a lot higher with the faster spins. Oh, all right. You okay?
I'm okay.
Maybe we could use like some gears or something like that.
Oh, yes, you know, that's a good idea because this circle that I'm making here, I can only go so fast. So
Yeah.
maybe with gears, you can do 1 circle here equals like 10 circles on the other gear.
Exactly.
Yeah.
Okay, so kind of like the gears on like a bike.
Yeah, the gears on a bike or something like that. A bike! Of course! Yeah, so we get a bike and we attach the back tire to the generator.
The generator, and then you can use the pedals of the big gear to power the small gears.
Okay, great. We'll go get a bike.
Yeah.
Yeah, high five. All right. Oh, right, they're over here. This is a generator. It generates electricity when you spin it. But how does it work? What wizardry is inside? Well, actually, generating an electric current is fairly simple. All you need is 2 things. First, you need a conductor, like this coil of copper wire, and you need a magnet. Now, this is a galvanometer. It measures small amounts of electric current, and I have my copper wire attached to it. Watch as I put the magnet inside the copper. I get a little bit of an electric current, and then I take it out. It goes in the other direction. A little bit going this way, and then I take it out, a little bit going that way. Positive, negative, positive, negative. This kind of current that goes back and forth is called alternating current, or AC. It's the same kind of electricity you have in your house. But here's the cool thing. Watch this. I put the magnet in and I leave it. It goes back to 0. You only get electricity when you move the magnet. All right, so let's create our generator. Instead of starting with a copper coil like this, what if we just had the magnet and we have it staying still, like that, and we move the conductor past it, like spinning? It's good, but not great, because we're only getting a little bit of electricity as it passes. So let's make it more efficient. Let's put in some more magnets. 1 on either side, and 1 on the top. And now when we spin it, it goes past all of these magnets, and every time we get a little bit of electric current. Well, this is how a generator works. If you take an electric motor or a generator apart, you can see there's a coil of copper wires on the shaft, and it spins around like this. And on the inside, there are magnets. So there you go. When you put it together and spin it, you get an electric current. Or if you put an electric current in it, it will spin, just like an electric motor. And that is how a generator works. Anthony and I are trying to create as much electricity as we can using just human power. But so far, it hasn't been going so well. It all comes down to how fast we can spin the generator.
Maybe we could use like some gears or something like that.
In order to get it spinning really fast, we're gonna use a bike. It's just a matter of getting a bike, taking off the wheel, putting it on a stand. It is now a stationary bike. It'll be even more stationary once we screw it down. And attaching the generator. All right, the bike generator. Bike-erator, what should we call this thing?
Bike-nomator.
Bike-nomator. I like it. So, okay, let's go over what we've got here.
Okay, so we've got 2 gears. We've got a big one, we got a small one. We turn our pedals, and the big gear turns the small one.
So this is the whole point of this build, is so that we can get
one revolution here means a whole bunch is spinning there. Exactly. The more we get here, the more our generator spins and the more electricity we get. We get tons.
Awesome. And obviously using bike, because you're using your legs.
The strongest muscles in your body.
Awesome. Okay, so now what's with this horn? That is a loud horn.
I know, I tried to warn you.
That is great, I love that.
So Anthony and I hop on and give it a pedal. We pedal as hard as we can, and we produce a pretty good amount of electricity.
How much electricity did they produce?
We got up to maybe like 18 there. You did a pretty good job.
That's enough for a power tool, like a drill.
It's good, you know what? This works well, I think, for keeping a good number for a long period of time.
Yeah.
So we can get up to like 18, 20, but it doesn't, we can't really get any higher than that.
Yeah, you know what we need is like one really hard pull, like all of a sudden. That way you can get like a spike.
Yeah, you're right. So it's like instead of putting all that effort into it going for a long time, you put all the effort into one quick motion.
Exactly.
Yeah, good idea. So you wrap a rope around here and then you just pull it.
Exactly.
And that'd be a really fast motion. Spin it really quick and get a very high number.
High spike, exactly.
Okay. You know, we're gonna have to take the bike apart though.
Okay,
all right. Well, it's science.
Okay, cool. So I'll just get.
Oh, you know what? We actually don't have to take the whole bike apart. We just have to take the generator off.
Oh, right. Okay.
Okay,
Hang on a sec. I got it.
And maybe we should attach the horn to the next thing too.
No! Turn it off! It's so loud!
So you want to generate some electricity. But what do you choose to generate that electricity? Hydro? Nuclear? Coal? Solar? Who knows? I do. I know. And soon, so will you. In order to generate electricity, you need to turn the generator. Turn the generator. One of the most common ways to turn the generator is to use one of these. It's a steam engine. Usually they're a lot bigger. You see, you heat the water to boil it and turn it to steam, which works a piston, which turns the generator. Huh? Pretty amazing, right? But what it really boils down to is heating water to make steam. Boil water to make steam to turn the generator. Coal power. Burn the coal to boil water to make steam to turn the generator. Natural gas. That's different, right? Nope. Burn the gas to boil water to make steam to turn the generator. Nuclear power. That's different, right? Nope. It creates heat, which you use to boil water to make steam to turn the generator. Wind power. We don't even need heat for that. Just use the wind to spin the fan to turn the generator. Hydropower. Just pour water across something that spins to turn the generator. No matter what, making electricity always comes down to turning the generator. It's always yada yada, yada yada, turn the generator. Except for solar. Solar does not work like that. But other than that, it's always yada yada, yada yada to turn the generator. And now you know your electricity generation. Hey, Ramona, you wanna come and give me a hand over here? My arm is getting tired.
Whew, it is hot out here. Oh, in order to generate electricity, you need to spin a generator. Most forms of electricity generation work like that, but not solar. Solar panels like this one generate electricity from the sun's energy. So, how do they do it? Well, this is a solar panel. Okay, it's not really a solar panel, I just sort of put this together, but it works the same way. There are two plates, and on these plates are electrons. I've got golf ball electrons up here, ping pong ball electrons down here, but they're all the same thing. Now, this happy little fellow is a photon, energy from the sun in handy-dandy particle form. What happens is photons come from the sun and hit the top plate and knock some electrons from one side to the other, like this.
and that knocks over some electrons. Now, these extra electrons travel up a wire in the form of electricity, and we can use them to do work for us. Then they change to the other charge, go back, and we start the process all over again. That is how solar panels work. But remember, it only works when there's sun and photons. Anthony and I are trying to generate electricity using human power. Spinning the generator didn't work too well, but we found if we used some gears, like those on a bike, it worked better.
You know what we need is like one really hard pull, like all of a sudden.
Using gears is a great way to get work done. The good news is there are generators with gears already in them. That means if we can turn the spindle once, the gears inside will spin the coil a lot of times. The only downside, turning the spindle gets harder the higher the gear. Anthony and I attach a spindle, and then we wind up the rope, which takes a while. Okay, so the plan is, it's on a big spool now.
Yeah.
And you just run as fast as you can.
Got it.
And we'll hopefully get as many revolutions as we can, depending on how fast your top speed is.
Okay.
Sounds good?
Sounds good. I can be pretty quick.
Okay, good. All right.
Ready?
On your mark.
Uh-huh.
Get set.
Uh-huh.
Go.
How much electricity did they create? 24 volts.
Actually, not bad.
That's enough to power their own personal scooter. Not too shabby, boys.
We need like a hard pull all at once.
Yeah, from something like really big. So what if we could get like really high, like up there? Could we attach the generator up there? You could jump down from there.
And I would hang on the rope?
Yeah.
Yeah, it's good, but I don't want to jump from up there. Oh, what if we put a pulley up there?
That
and
would
then the
work.
rope goes through the pulley and then back down, and then I jump from somewhere much safer, like just on top of here onto a crash mat or something.
That sounds great.
And that's my full body weight on the rope.
That sounds great.
All right, high fives.
Yeah.
Tidal power in 60 seconds. By now you know that in order to create electricity, you need to spin a generator. Scientists and engineers are always coming up with lots of new ways to use natural forces of the Earth to spin a generator and create electricity. One of those natural forces is the power of the tides. You see, the water in the oceans doesn't stay still. Every few hours, the water, or the tide, goes out. And then a few hours later, it comes back in. So if you attach a paddle wheel in the water and attach that to a generator, when the tide goes out, it creates electricity. When the tide comes back in, it creates electricity. That is how you create electricity using the power of the tides. It's water power. In fact, hydroelectricity is also using water power. Do we have time to talk about hydroelect? We don't have time? We don't. Okay, maybe come back. Hydroelectric power in 20 seconds. 20 seconds? Okay, hydroelectricity comes from water. Hydro means water. So all you have to do is find a place where water pours down from a height. And you can put a generator in there, and ta-da! You're creating electricity with the power of hydro. Ha 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 ha! I did it. Anthony and I have pulled and pedaled, and now we're going to hang on to the rope and use our whole body weight to spin the generator as fast as possible. Okay. Crash mat. Let me test it out.
Looks good.
Yep, it's good for crashing. So I go up here. Okay, I go up here.
Climb on up. We'll get you the rope. Got your helmet for safety.
Helmet for safety, crash mat for safety. So we have the rope, and it goes up through that pulley, and then back down to our generator with a spindle on it. And as I fall, the spindle will turn.
Exactly.
And hopefully the speed of me falling and holding and yanking it down as hard as I can will be the biggest spike of electricity yet.
That's right. We'll be measuring it on our multimeter.
Okay.
Okay.
Ready?
You ready?
Yeah.
Here we go. 3, 2, 1.
I jump down and my whole body weight pulls on the line.
Oh, that was awesome. That was like our biggest spike ever. That was amazing.
All right, high fives. Biggest spike ever. Is it enough to power my house?
Nope.
How much electricity did Phil generate? Almost 30 volts. How much does he need to power his house? 120 volts.
he's still off by quite a bit.
Well, we've learned something. Nuclear, wind, hydro, solar, natural gas, coal power.
It's all great ways to generate electricity.
Yeah.
And human power,
Not so much.
not as good. But human power is more fun.
Yeah, way more fun.
Yeah, so your turn?
Yes!
Okay.
Give me,
You take the helmet and I'll take the multimeter.
Okay.
And then we'll go and we'll do it again. Okay. Wait, I gotta wind it up. Greetings, Science Maximites. My name is Phil, and welcome to Science Max Experiments at Large. At this very moment, half the lab is being held together with the power of electromagnets. Magnet 1 turning off. Electromagnets are a really cool and powerful way to interact with the world. And when I say power, that's because you need power to make them work or not work. Magnetism is an invisible force that has to do with the magnetic fields created by magnets that lets them attract things that are metal or each other. But electromagnetism is a little different. You see, magnets are magnets all the time. It's because of what they're made out of. Electromagnets are only a magnet when you have an electric current going through them, which means you can turn them on or off. Today, we're gonna be building an electromagnet. Oh, that was the wrong switch. Anyway, like I was saying, today we're gonna be building an electromagnet.
You need a bunch of copper wire, a very large nail, or something metal to become your electromagnet, electrical tape, a battery, an on-off switch, wire strippers or a craft knife, and the help of an adult, and finally, something to magnetize, like these paper clips. And remember, all of the steps for this experiment are on the website. To begin, take the copper wire and start at the top of the nail. Leave a little bit of wire sticking out, then carefully start to wrap the wire around the nail. Don't go all the way to the end because you need some metal to turn into the magnet. Instead, when you want to start again, run the wire straight back to the top and start wrapping again in the same direction.
And keep wrapping and wrapping until you get to this. Now, I've used some electrical tape here, and here to hold it all together.
Using your wire strippers or a craft knife and the help of an adult, remove the plastic coating from the ends of the wires. Attach these wires to the wires from the on-off switch with electrical tape, or attach them directly to a battery if you don't have an on-off switch.
And ta-da, you have an electromagnet with your on-off switch. All you need to do is take the things you're going to magnetize, turn your electromagnet on, and suddenly it becomes a magnet. Pretty amazing, ha 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 ha. And then you can magnetize to your heart's content. But when you're done, don't forget, you want to turn it off. So that's what we're gonna do today on Science Max Experiments at Large. We're gonna max out the electromagnet. So, where's my lab coat? Oh, there it is. We're gonna see how big we can make an electromagnet. And when I say we, I mean me and an expert. Let's see. Oh, Heather from the Ontario Science Center. She knows her way around magnets. So let's see. Yeah. I wonder if she's busy. Well, let's find out.
And after we're done, I'll need to come back and clean up the giant mess I made in the lab.
Hey!
Hi, Heather, how you doing?
Good to see you, Phil.
I was just wondering if you could help me with something. Are you busy?
No, I got time.
Okay, great, because I'm gonna make a giant electromagnet experiment and I need your help.
That sounds like a lot of fun.
Okay, great. Let's go back to Science Max headquarters.
Oh,
we'll
via
take a-
the portal?
Yeah, by the portal.
Okay.
You sure? I
Yeah.
know you're hesitant, so I want to reassure you, nothing will go wrong.
Great, okay.
Okay. Oh, hey, we're here.
We're outside.
It's okay, it's
no,
okay. Don't worry about it.
No,
No,
I think
It's fine, it's
definitely.
fine, it's fine.
You all right?
Yeah, I was supposed to come in over there, but I came in over here. Oh well. So today, Heather, I want to max out the electromagnet. Turn it on, and it's a magnet.
Pretty good.
And turn it off, and it stops being a magnet. I want to make this into a much bigger, maxed out version.
All right.
So what are some of the things we can do to do that?
Well, actually, if you have a larger battery, one that has a higher voltage, we can try that for sure.
Okay,
that
so
will help.
there are batteries that are 12 volts?
Yes.
We could try one of
Give it
those?
a try,
I think
for
those
sure.
are like bigger, right?
Yeah, bigger, more powerful, absolutely. Now, that's one thing you could do. You can also increase the number of wraps of our coil here.
So how many times we wrap that wire?
Yes, we'll increase that magnetic field, making our magnet stronger.
And of course the nail, which is important because that's the thing that eventually becomes the magnet, right?
Right on, yes.
So what I thought we would do is we would start with a bigger nail.
Oh.
What, right? So larger battery,
Yes.
more voltage, and a lot more wraps of the wire.
Right on, and we have more space for that now, which is smart. Good job.
Great, okay, so we'll get to work.
Great.
Max Historica.
If you've ever seen a compass, you know that the needle points north. That's because a compass needle is a magnet, and it points towards the Earth's magnetic North Pole. And I'm using this compass to try to get to the North Pole. But it isn't easy. In fact, scientists knew there was such a thing as the North Pole as far back as the 16th century, but no one was able to actually get there on foot until 1927. You'd think it wouldn't be that hard, right? I mean, the needle points you straight there. Just follow the needle, right? But now that I'm here, I realize it's really difficult. I mean, the wind is incredible and the snow is intense and it's so cold. My hands, yeah. So, okay, we're not really at the North Pole. We were just sort of recreating that. But still, I salute the brave explorers who tried to make it there in the name of science. And I got a sense of it because the wind from the fan and the fake snow was, okay, everybody, let's pack it up. I mean, that was pretty good. I just didn't know about that other camera.
So, back to our main experiment, where Heather and I are building a larger electromagnet. An electromagnet works like this. When an electric current is traveling through a wire, it creates a magnetic field. If you wrap that wire around something ferromagnetic, that's something made out of a metal that is attracted to magnets, like an iron nail, then it becomes a magnet. You can make a magnet stronger by wrapping more wire, which gives more distance for the current to travel, increasing the magnetic field, and you can also increase the strength of the current. Heather and I start with a coil of 30 meters of wire and start wrapping. And wrapping. And wrapping.
There, the wire is now all done. And remember, if you're doing this at home, do not use a drill unless you have an adult to help you out because drills can be very dangerous. This one goes at a very slow speed, so it was okay. But yes, definitely an adult supervised activity.
Then we attach another on-off switch and make some leads that connect to a 12-volt battery. So, more wraps of wire and more current means the electromagnet should be stronger.
Okay, so we're gonna try this electromagnet and we're gonna pick up this stuff right here.
Great.
Ready?
You ready?
Yeah.
3,
2, 1, go! Is it on?
Yeah.
Wow, it really does, you can't tell it's on, but.
No, but bring it closer and...
Oh yeah, look at that. Okay, we
That's
turn
fine.
it off.
All right.
Let's see if this nail can pick up this nail.
All right.
Ready?
Ready?
Go. Oh. Okay, how about this side? Oh, no. No.
I don't think we're strong enough.
It's not strong enough. I think that we need to max this out even more.
Even more?
Right.
So I'm thinking there are a lot of appliances that use electromagnets, meaning it's already set up, it already has tightly wound coils and high voltage. So we're in a lab here. Maybe do you have old appliances around?
I have parts bins with a whole bunch of stuff. Maybe we could find some electromagnets in those.
Let's do it.
Okay, great. Let's go. All right, pliers, battery, copper wire. Now, if you've already done the electromagnet experiment, here's another experiment that uses all the same materials plus these. Ha! Neodymium magnets, some of the strongest magnets you can get. So, here's what you need.
A battery, some neodymium magnets the same diameter as your battery, copper wire, and some pliers.
So here's what you do. First thing is you put the batteries and the magnets together, like that. Then what you want to do is bend the wire so it's touching the top of the battery and goes around the battery and then touches the magnets at the bottom. Here's what that might look like. I say might because you can do any shape you want. I've made a coil here, and if you put it over the battery, you'll see it only touches the very top of the battery and the magnets at the bottom. And if I let it go, it spins. It's a homopolar motor. What happens is the battery sends an electric current through the copper wire, and that turns it into an electromagnet, which is attracted to the magnets at the bottom, and it spins. So now let's max it out. Aha! A D-cell battery, which is larger and, of course, larger neodymium magnets. And you do the same thing. Make a coil that only touches the battery at the top and at the magnet, and ha-ha! It spins! Maxed out homopolar motor. But don't worry, this is not the biggest size we're gonna do. Come on. Maxed out homopolar motor. I have 27 D-cell batteries, a giant copper tube, and a neodymium magnet. So I'm just gonna, and then we get rid of that. Put this down. Okay, so the first thing I do is attach the neodymium magnet to the batteries. And I've got all the batteries taped together here so they'll sort of stand up like this, huh? Giant stack of D-cell batteries. Okay, now what I do is I take the copper coil, I take the copper coil, I need to get, okay, hold on, I got this. I just need to get the copper coil there. I did it. Okay, so I take the copper and I put it on top of the D-cell batteries like this, and then I let it go. Let it go. Nope, whoa. Homopolar motor. Okay, so that didn't work, but that's okay. I like it when it doesn't work, because that's science. It's not science if it works perfectly every time. I mean, you gotta have some room for improvement.
Heather and I built a larger electromagnet, but it still wasn't as powerful as we hoped. So now we're searching for parts that came out of an appliance that are pre-built electromagnets.
What about this?
I think that'll do the trick.
Do you think that does look like an electromagnet, huh?
It does, yeah.
And there's a whole big bunch of copper wires coiled on
Coiled
that.
around.
So you think we can use this?
Yeah, let's try it.
Okay, great.
We built the next version of the electromagnet. This one already has the copper coils, so it's just a matter of attaching wires and an on-off switch, and attaching all of it to a 12-volt battery.
Do you think 12 volts will be enough?
Let's find out. I think so.
Try that.
Once we do, it works much better.
Oh, no problem at all.
Ready?
Yep, turn it on.
On.
Whoa, pretty good. Okay, off.
Off.
Neat. In case it was really strong, I have the next step. Horseshoe. Okay, ready? Oh, whoa, that's...
Here.
I can't pull that off. Okay, wait, grab this. Okay?
Work together.
Yep. So that's passed all of our tests.
Yeah.
This is really strong.
Is there a way to test it further?
In order to test how strong our magnet is, it's as easy as seeing how much weight it'll lift. Heather and I find a metal table.
All right, Phil, so I brought the electromagnet.
Okay.
Just put it right here.
Yep. We add some sandbags for more weight and then attach a scale so we can measure how much weight we're lifting. We use a chain hoist, a simple machine made for lifting heavy things. This one can hold up to 454 kilograms.
Want to turn it on?
We're ready?
Yep.
Here we go.
You can read on the scale how much weight is being lifted.
And that scale is going up.
Pounds on this side, kilograms on this side. We keep lifting until...
Oh! Okay, so how much did it hold?
It held 100 kilograms.
Oh, that's more than I weigh, which gives me an idea. Come on.
This is ferrofluid. It is ferromagnetic, which means it's attracted to magnets. And I know what you're thinking. You're thinking, it's not that interesting. Well, watch as I put it next to this magnet. Very interesting. And because it's a liquid, it behaves in very interesting ways. Watch this. Unlike most things ferromagnetic, like paper clips or iron filings, ferrofluid is a liquid, which means it behaves in a unique way. The spikes it creates are following the magnetic field lines of the magnet. You can see the magnetic field in 3D. It's even more impressive when we max it out. This is ferrofluid outside of a glass jar. Now, it's sitting in a pool around this electromagnet. And this is a dial which I can use to change the voltage of the electromagnet, making the magnet stronger. Watch this. Changing the current going to the spiral in the middle turns it into a magnet. The more current I put in, the stronger that magnet becomes, allowing the ferrofluid to climb the spiral to the top. And remember, even though it looks all spiky, it's still a liquid. I will demonstrate with my plastic spoon. And watch this. When I turn the magnet off, it stops being spiky. Turn it on. Turn it off. Science.
The Wizard Academy. All you have to do is demonstrate true magic. And you will be granted entry. Well, Fuzzix, who is the next applicant for the Wizard Academy?
Overwhelmo.
Indeed, it is I, Overwhelmo. And prepare to be overwhelmed. Would you be flabbergastified if I balanced this coin on its end?
Not really, no.
But would you be impressed if I was to balance this coin on top of this coin?
Possibly.
Prepare to be flustered and stupefied. Stupeflustered as I balance 3 coins on their ends on top of this glass.
Well, that certainly would seem like magic. Let us see.
Okay. No pressure, Overwhelmo. You can do this.
And now, I say, a magic word.
A magic word! Ha 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 ha! And now you must let me into your academy.
Wait. What's under the cloth?
What cloth? This cloth? Nothing. Oh!
Is that a magnet?
This? No!
The pull of the magnet is what's keeping those coins up. The magnet is just strong enough to keep the coins from falling.
No, this is set dressing. It's just
It was a good trick, but it's science, not magic.
Well, yes. And you will see! You will see! I will be back! I, Overwhelmo, will return! And I will do such magic that you will need extra socks, because I will knock them off with my magic. You will need at least 2 pairs of socks, maybe 3 pairs of socks.
We can still see you.
No, you can't!
So back to our main experiment. Heather and I have created a very strong electromagnet that can hold a lot of weight.
It held 100 kilograms.
Oh, which gave me an idea.
All right, you ready?
Let's do it.
Electromagnets super maxed out experiment. We've got
2 electromagnets, 1, 2.
and those are wired to 2 batteries, which are on my belt, just like this, so that I can carry them around. And we've got a crash mat here, because
We need to keep you safe because you're gonna be using these electromagnets to get across this massive beam above us.
that's right. I'm gonna stick to this metal beam and go across with the electromagnets.
Wow.
We hope.
I have faith.
I'm glad you do. I've got helmet for safety, goggles for safety, gloves for safety, but in this case, sometimes a lab coat is more safe and sometimes it's less safe. This time, it will get all caught up, so no lab coat. All right, you ready to go?
I'm ready, let's do it.
Okay.
Oh my goodness. What?
Okay. Because each of our electromagnets can hold more than my whole body weight, I can use them to cross the beam. When they're on, they stick like, well, magnets. And when I turn them off, they stop being magnets and I can move them along as I go. Now, this is something you should definitely not try at home.
Come on, Phil. You're almost there.
We did it! Yeah! There you go, Science Max, experiments at large, electromagnets! You wanna go?
No.
You sure?
I'm positive.
Okay, I'm going again. Woohoo!
Crazy.
Greetings, Science Maximites. My name is Phil, and this is Science Max Experiments at Large. Whoa. Oh, I better spin the other way. Today, we're gonna be taking a closer look at spinning. Well, all things spinning. Spinning, rolling, rotation in all its forms. And, when things spin, they're subject to a whole bunch of different forces. And some are strong enough to even counteract gravity. So let's get spinning! Oh. Okay, let's get spinning! We are going to make a gyroscopic whirligig, and it spins, and I don't, which is a good thing. Watch this. You pull the string, and it spins, and it stands on its end. Why does it stand on its end when it spins? Because of angular momentum, which we'll get to later. And here's how you can make one of your own. You will need some craft sticks, string, a small zip tie, a shish kebab skewer, spacers like these wood blocks, and finally some round discs, which you can cut out of plastic or find from parts of broken toys. Now, if you want to research this yourself, look up Gyroscopic whirligig. Get 2 craft sticks and glue them to your wooden blocks just like this, and then do it again. Space them apart and glue them to crosswise craft sticks, and this will be your launcher. You put your hand in the small end, and the longer end here is where you put your gyroscopic whirligig. Now let's make that. What you want to do is you want to take a shish kebab skewer or whatever fits the diameter hole of the round things that you're using. I like to use little plastic discs from, these are from remote control mechanisms, but you can use anything you want. I found that this launcher works best with 4 discs of the same size. Just like that. Space them out evenly, glue them down, and cut the skewer even on both sides. Then add your zip tie. Put it right in the middle, tighten it up, and cut off the dangling end. This zip tie just gives you somewhere for the string to hold on when you wind it up. Now for your pull handle. Glue 2 craft sticks and 2 wooden blocks, then 2 more craft sticks on the sides. Then tie a string to the middle, wrap that string around the middle of the whirligig, and aha! You have a gyroscopic whirligig, a pull handle, a rope, and your launcher. Now remember, you put your hand in like this, and you fit your gyroscopic whirligig in just like that, and you pull towards you, and it spins! Oh, and that's what we're gonna be doing today, Science Maximites. We're gonna max out a spinning rig, something like this. It's gonna spin bigger, faster, more weight. It's gonna be totally maxed out. So come on. But first I need an expert to help me out. So, let's see here. Wait a minute. Aha! Perfect. Come on, this is gonna be great. Okay, this is it. Hey, Silena from the Ontario Science Center. I'm really glad you're here. You're gonna help me max out the gyroscopic whirligig.
The what?
Oh, the gyroscopic whirligig. Here, I'll show you. It's this, and it spins, and what works on
Phil, where are your shoes?
I think these are my shoes. They must have changed into flippers in the portal.
Did
Weird.
you want to change them?
Yeah, I'll be fine. Anyway, like I was saying, the gyroscopic whirly gig is really good. Let's do it here so that I don't have to walk as far.
Can I see it?
Yeah, here it is. Ready? You spin it up, and it spins, and it goes for a while, right?
Because you made it out of 4 discs, it probably spins better because there's more mass.
Oh yeah, because you know what? I actually have an old one. Yeah, I got an old one here with 1 disc, and it does not spin as long as the 4-disc one.
Could we test the 1-disc one out and compare it to the 4-disc one?
You bet, because you know what that is? Science.
Science.
Yeah, that's science. Okay, let's try it. Ready? Whoa.
Huh, look at that. The 4-disc one spins better longer than the 1-disc one because the 4-disc one has more
mass, therefore more inertia. So when we max it out, we should get something with a lot of mass.
Yeah, more mass.
Wait, I have something. Right. Whoa. Can you give me a hand?
Careful, Phil. I don't want you to fall.
Yeah, well, I don't want to fall either. It's hard to walk in these.
I can imagine. That's why I asked you if you wanted to change your
Nah, we're
shoes.
fine. I'm fine. Okay, check it out. This is what I was going to. Okay, this is what we can make it into our maxed out spinning gyroscopic. Why not?
It's just, look at how big the hole is.
Oh, yeah, because we're going to need something to be the axis, huh?
Yeah, we need like a tree to fill that. I don't know
Yeah,
if
you're
it's
right.
gonna work.
Too big. Is there anything else wrong with it?
It's also kind of light. It's not that heavy.
More mass, better.
More mass.
Okay, tell you what. Oh, I know. Hold on. I know. Whoa.
Oh, that looks perfect.
Yeah, and then we got this pole.
To go through the center?
We'll go through the center like that.
Awesome.
And then we'll just weld it together, and there you go.
This will be great.
Yeah, high five.
Phil.
Okay, no, wait, sorry, yeah, you got the thing.
High five.
Well, now I got the thing.
Yeah.
All right, I'll get new shoes, and we'll work on our high five. Now it's time for one of my favorite scientific terms, the Magnus effect.
I am Magnus, and behold my effect.
No, the Magnus effect has to do with things that are spinning. Things like these cups. And here's a great little Magnus effect flyer you can make at home. It's super easy. Get 2 styrofoam cups and tape them together at the bottoms using science tape. Then get some elastic bands and make a long one by tying them together. Take your elastic and you wrap it around the cup like this. Then hold the elastic on the bottom, remember, like that, and then let them go. They fly up and out. The reason why it goes up and stays in the air is because it's spinning, creating moving air over the top. Moving air has lower pressure, which means it's pushed up by the higher pressure underneath. And that is called the... Oh, come on.
Now, the Magnus effect.
Yes. So, let's max it out.
Magnus it out. See how much better that sounds?
No. Max it out. Check it out. Magnus Flyer 2.0 stand elastic slingshot. Wrap it around. Remember, for the Magnus effect to work, your cups need to be spinning this way, the front side rotating up.
Oh, and there you have it, the Magnus effect. I, Magnus, am now taking over the show. It is now Science Magnus. That is my effect, slightly improving the name of science TV shows. Science Magnus.
Silita and I are maxing out our spinning top. Based on our small version, we decided to make one with as much mass as possible. So we got a 20-kilogram weight and welded it to a metal shaft. Will this work the same way? Well, let's look at the science. Why does a top spin? Well, let's start with Newton's first law, which is an object at rest tends to stay at rest, an object in motion tends to stay in motion. But the in motion has another part. That object also wants to go in a straight line. If you think of a bowling ball rolling along, it would need another force to act upon it to make it change direction. We say that a moving object has momentum. Now, a top doesn't go in a straight line, it spins around, but it still has momentum. It's an object in motion, and even though it's spinning, it still does want to go in a straight line. It's just that that straight line
is here. We call this angular momentum. To make a top move this way or that way would take an outside force, so it stays upright as long as it has enough momentum. But when it slows down, there's less momentum and it becomes harder to resist external forces, like gravity, which will eventually want to make it topple. Our top has a lot of mass, which means it'll have a lot of angular momentum when it gets spinning. It's just a matter of getting it spinning fast enough.
So should we spin it?
Yeah, let's spin it. Let's see if we can get it to work. Hey, okay.
Spin.
Oh, we're gonna let go. In 3.
Wait. I can't get it.
1.
Wait.
Okay.
Okay. Not fast enough.
We need something to help us get it spinning faster. Maybe a rope?
A rope, yeah.
Wrap a rope
That
around
was
it
my
like the-
idea too, a rope, because the small one uses a rope.
Yes.
Okay.
Okay, I'll go grab a rope.
So, wrapping the rope up.
I'll let you wrap the rope
Okay.
up. I'll get my holder back on top.
Spin it counterclockwise.
We attach the rope and wind it up.
You want to make it super clean. This is some of the best coiled rope I've ever seen. I'm gonna pull the rope. You're gonna hold on to it, but I can't pull really hard because you won't be able to hold it up. Because we don't have to pull hard. We just have to get it going fast.
Yes.
Silita keeps her hand on the block at the top and I pull.
Ready?
Wait a minute. We'll get all the way. Oh. Whoa!
Spinning a lot better than I thought it would. It's still spinning, but it's wobbling.
Oh, careful.
Oh, there it goes.
It works, but just barely.
It might spin better. It might spin straighter.
Yeah.
If we had it spinning, something help us spin it faster.
Yes. Faster with more power.
With more power.
This is a string. You can pull a string, but you can't push a string. Well, you can. You can push a string. You really can. Okay, quit it. Quit it. This little contraption works sort of like a baseball pitching machine, but in miniature. See, there are 2 motors here, and the wheels spin together to shoot things out this way. Things like this craft stick. Watch this. Whoa! Let's watch that again. Whoa! But now, watch as I put a large loop of string through. What? Pushing string. How does this happen? Hello?
I don't suppose it's the Magnus effect?
No, it's not the Magnus effect.
No, it's all right. I'll be in my lair if you need me.
Okay, right. Bye. Right. Where was I?
I believe you were at, the reason why this works is...
Right. Pushing string. How does this happen? It's all because of inertia. Check it out. The wheels are pushing the string through fast. It's got some weight and it's got some speed, which means it has some inertia. So when it goes this way, it wants to keep going this way. But it goes all the way to the end, and then because it's a loop, it gets sucked back in this way, which means all of this inertia, you can sort of overcome gravity. Pushing string. Science.
Silita and I need to get our maxed out top spinning faster. We tried a rope, but now we're trying a drill. We get a wheel on our drill and use it on the outside of the weight to get it spinning up.
A little faster.
Oh, it's wobbling now.
A little more.
Push me.
And release.
It's kind of cool that it wobbles that much and it doesn't hit the ground.
It worked better, but there's always a way to max it out even more.
You know what we need, Silita?
What do we need, Phil?
A maxed out drill. Put it right on the top here and get it spinning very, very fast. Super maxed out gyroscopic whirly gig. Is it just the top now?
I don't know. Do you
We
want to
could
be
call it a
gyroscopic?
gyroscopic. Well, it's sort of a toppy, kind of gyroscopy. This is a bike tire. It's pretty light, but I still can't hold it from the end of the pole like this with one hand. Nope. But I can if I get it spinning fast enough. I just use this drill, and then I get... Okay, so this is gonna be awfully hard to do with one person. Oh, this is the perfect opportunity to use the Trevor button. Trevor button. Hey, Trevor from the Science Max build team. What are you doing?
Maxing this out.
Oh, right on. Can you give me a hand for a second?
Sure.
Awesome. Okay, so you take this drill, and we're gonna get this wheel spinning really fast.
Okay. I don't know if it's,
No, I don't wanna know.
I don't know if I remember to...
No, it's fine. Max it out. We gotta max it out. So, because it's spinning, I can hold this heavy weight in the air.
How is this possible? Because the wheel is basically a top. The forces that prevent a top tipping, angular momentum, are still working here. This angular momentum resists a change in direction this way, which is how gravity would want it to tip. Interestingly, these same forces also keep it spinning around me in a circle.
So, I can lift a heavy weight in the air just by spinning it. Awesome max out experiment, Trevor. Yeah! What was that?
It's my science confetti high five I just made.
Well, you know what we should do?
What?
We should max it out. Yeah, we can make a giant one and then a whole bunch of confetti in it, and then people like jump up and do more confetti that would come out, right? And then so what would happen is there would be all this Trevor?
Silita and I have maxed out our spinning top. The trick is getting something that heavy to spin really fast. We've tried a rope and a drill, but now we have a maxed out drill.
So more power and more speed, which is perfect for spinning this massive top.
Yes, and perfect for maxing out anything.
We get it spinning and it works great. The top spins for a really long time. In fact, its mass was so large, it started drilling a hole in the concrete floor. We tried it again, but started to notice something.
The drill is smoking quite significantly.
Our drill began to overheat. Why? Good old Newton's first law. An object at rest wants to stay at rest, and an object in motion wants to stay in motion. The more mass we have in motion, the longer it will stay in motion.
This will go forever. Well, not forever,
Well, not
but
forever.
it'll go a really long time because it's got a lot of weight.
But that same mass wants to stay at rest when it's not moving. We have to overcome all that mass wanting to stay at rest to get the top spinning. And even for our maxed out drill, that was a tough job. But once it was spinning, there was only one thing to do. Max it out even more! Silita and I come up with a plan to max out the top by riding it.
You want to ride the top?
Of course I want to ride the top.
We can both ride the top. One person's gonna have to drill this, so we'll have to take turns.
Max Historica. This is Leonardo da Vinci, one of the greatest scientific minds the world has ever seen. And this is a wheel. Da Vinci thought to himself, wouldn't it be great to design a wheel that kept spinning forever? So he got to work. Something that keeps spinning forever without stopping is called a perpetual motion machine. And it was an obsession of Da Vinci's. Why, this is great. The bottles tip the water to the outside, making one side of the wheel heavier, which will keep it spinning forever. Except it doesn't work. You see, what Da Vinci doesn't know is that science says a perpetual motion machine is impossible. But of course it wasn't for another 350 years till scientists figured that out. So we can't tell Da Vinci. What? Oh, never mind. Leonardo da Vinci, one of the greatest inventors ever. Even if not all of his inventions worked. Silita and I got our maxed out spinning top to work pretty well. The only thing left to do was to ride it. We attached a large disc and a Lazy Susan. That's a platform that spins around on ball bearings.
Lazy Susan on top,
Lazy Susan.
so that you can ride on it.
Yes, and then we wanted to add this extra bit. Now, why did we want to add this?
We need a little bit more weight on our top.
Okay, so who gets to ride it?
I feel like you should ride it.
I think you might be right.
Because I want to use
Oh,
the drill.
the super awesome maxed out drill. Okay, so let's do it. First thing I should say is do not try this at home. We are trained scientists.
Silita uses the drill to get it spinning while I hold it steady. Then I hold on to our safety line above and carefully rest my weight on the top. It works, but not for long. We take turns trying it out, but it seems we have another part of science working against us. Good old friction. Friction with the air and with the ground is what eventually slows a spinning top down. But our weight on the ball bearings of the Lazy Susan really increases the friction. More friction means the top slows down a lot faster.
Whoa!
That was pretty cool.
It was kind of terrifying, right?
Yeah.
Good old Newton's first law kept the top spinning, angular momentum kept it from falling over, and friction slowed it back down. The forces were always the same, no matter if it was a little top, a maxed out top, or a rideable one.
Yeah! Whoa! There you go. Nice, Max. Experiments at large, giant spinning top. That's as large a spinning top as I think you.
I think in the entire world.
Let's do it again. Yeah!